Okay, so I hope all of you have opened your IS 456. So first, I will tell you what is limit state. Okay. Okay, so now I'm going to share the screen. And I hope all of you can see the screen. I hope all of you can see the screen. Okay. Okay, as you can see, limit state means this method is an advancement uh, over your working stress method. Okay, so in working stress method we have designed we have considered only up to the elastic region. Okay, and I think I have shown you the curve of concrete as okay. So let us see this. Okay, let us see this curve. Okay, so this is that I will explain this curve later on, but just for your understanding I am telling you now. In working stress method we have considered this strain curve for concrete or is an elastic one. Okay, please unmute yourself. All of you, please mute yourself. Yeah, okay. So in working stress method, what is our first assumption? The main assumption was that the stress strain behavior is elastic. Okay. But actually, after doing experiments, after going through after doing a lot of experiments, we have seen that the stress strain behavior for concrete as well as steel, they are not exactly elastic. Okay. So we will get some elastic region as well as we will go beyond that, which region is known as your plastic region. So in limit state method, we will consider the detailed stress strain behavior of concrete as well as steel. But in working stress method, we have assumed that the behavior of steel with respect to loads is linear. That means it is showing elastic behavior. That means if you remove the load, it will go back to its original position. But actually, in actual practice, it doesn't happen. Okay, so that is the main drawback of our limit state method. Okay, so let us see here. This is an advancement over traditional design method, and it is also known as plastic design method, because in limit state method we will consider the plastic region also. Plastic region means after putting the load, when as soon as you for some time you won't see any deformation in that structure. Okay, but after some time you will see that it is start to deform. Okay, it will start to deform. If you remove the load also, then also the deformation will remain same. So in that case, at that particular time, you can say that the deformation is plastic. That means it is your permanent deformation. Okay, so in limit state method we will consider that plastic region also. That's why it is also known as plastic design method. Okay, so limit state method represents comprehensive and rational solution to design problem. Okay, so here you can see here, unlike the WSM means working stress method, which is based on calculation of working stress on material alone. Okay, but unlike this is ULM means ultimate load method. Okay, because I have given you the PDF also, or I think I have given you notes also. We have three different methods: working stress method, ultimate load method, and limit state method. Okay, and the best one is which we are currently using, which is our limit state method. So unlike ultimate load method, which is based on calculation on ultimate load condition alone, but in our limit state method we will consider both working stress as well as ultimate load. Okay, so that's why it is the best method. Okay, so now limit, what is the meaning of the word limit? I told you before also, and I think all of you know that. What is the meaning of the word limit? Limit means,
Sir, is it maximum?
yeah, it is means maximum. Okay, limit means maximum. So the aim of this method is that the structure should be able to carry all the load safely, and it must perform safely during its lifetime. And I told you before also that Benison. Okay, so in limit state method, whatever structure we will design, we will design that the structure must carry the load safely. Okay, means whatever loads will be coming to the structure must carry those loads safely. That is our first criteria in limit state method. And the second criteria is, after this step, the structure must give you satisfactory performance during its lifetime. Okay, so that is these are the two criteria in limit state method. So in limit state method we have two parts. One is related to safety of the structure, that means your structure must carry the load safely, and the second part is your structure must be giving you satisfactory performance during its lifetime. Okay, so in limit state method, here also you can see here, in limit state method, we will consider safety at ultimate load. That means our structure must carry maximum amount of load safely. Okay, and the second considered part is serviceability at working load. That means our structure must give you satisfactory performance during its lifetime. Okay, so here in limit state method, we will consider multiple safety factors for adequate safety and serviceability by considering the limit state. Limit state means maximum ultimate load condition. Okay, so here we will consider multiple safety factors for adequate safety. Okay, so next we will see how we will consider these multiple safety factors in the later part. I will show you now. So here you can see here, limit state means the acceptable limit for the safety and serviceability requirements before failure occur. Failure means when the structure will start showing cracks and all. Okay, then at that time you can say that our structure failure point has reached. Okay, so whenever your structure will show you some deformation, or you can see some cracks in the structure, then that is your failure point. So the limit state means the acceptable limit, okay, for the safety and serviceability requirements before failure occur. Okay, so now we have to see what are the different types of limit states. Limit state of collapse or failure. You can see in the IS code also, in IS 456 also, these things are given. Limit state of collapse or failure. So in this limit state of collapse, we have to discuss about these four things. Flexure means bending. Our bending must be within permissible limit. Okay, so compression. Okay, in limit state of collapse, we will see whether our bending will be within the permissible limit or not. What is the shear force? What is the bending moment? These things we have to consider. We have to calculate. Then we have to design the structure. Then uh, compression. Compression means, okay, so can you give me an example of a compression member? Anyone? Can you give me an example of a compression member in a building? That means whatever load that member will carry, that is mainly compressive. Can you give me an example? Can you give me an example of a member which is mainly carrying compression? Yeah, good, good. Shiroda, good. Column. Column is the main compression member, okay? Because whatever load is coming to the column, okay, the load is compressive in nature. Yeah, column is the main compression member. So in limit state of collapse, compression means we have to design columns also. Then shear. Shear means what we have to do here. Can you tell me what word shear means? In a building, we have to design the building for beams for shear also. So can you tell me what is shear? Means what we have to do there in that part? Can you tell me? Anyone? Anyone have any idea about limit state of collapse for shear? Shear means what we have to do there. Do you have any idea? Anyone have any idea what is in shear part, what we have to do? Okay, so do you heard the term stirrups? Anyone heard the term stirrups? Anyone heard the term stirrups? Anyone heard the term stirrups? No one? Huh? Okay, so from this time onwards, from today onwards, whenever you see some structure is constructing, you see all these things. You go to a site or any building, RCC, any RCC building. I think, not I think, I know lot of structure, lot of houses are constructing near your house. Okay, so whenever you are visiting that place, if you are passing by passing by the building, you just go near to the column or near to the beam. You just see the reinforcements, how they are placing the steel, how they are putting some vertical bars. Okay, so now I will show you some, okay, some images of a structure. Okay, then you will understand better. Okay, wait. Okay, wait for 1 minute. I will show you the some. I will show you some structures, not structures. I will show you some what is stirrups, what is these things. Okay. Okay, wait for 1 minute, okay? I will show you. Okay, so can you see the screen, all of you? I think all of you can see the screen. Yes. Okay, so see, this is the column. Okay, this is our column. This is the beam. This is the beam. I will show you the images also, but first you see the video. Okay, so now I will show the images also. Okay, you see this image. Okay, see this image. Okay, so this is our main beam. Okay, this is our main beam. Wait, I will download it and then I will download the image, then I will show you. Okay. Okay, I will show you now. Yeah, can you see the screen now, all of you? Can you see the screen?
Yes, sir.
Yeah, okay. See, this is our beam. Okay, this is our beam. See, these are our top bars. That means these are our tension bars. We are providing these bars in the tension zone. Okay, so what are those? Okay, I will show you. I will zoom it. Yeah. Can you tell me what are these things? This one, this one, this one, these things. What are these? This. Can you see the hand? Can you see my hand here? What is this? What is the name of this thing? Huh? Anyone? What is this thing? What is this thing? This. Can you tell me, anyone? Anyone? Rings. It is not. Yeah, in these labors and these mysteries will be called this as rings. But actually, the name, engineering name is, what is this? These are called stirrups. Okay, these are called stirrups. So from now on, you don't say rings, you say stirrups. Okay, from now on you will be saying this as stirrups, because these laborers, they don't know what is the name. They just say this is just like a ring. They, because of that, they say this is a ring, these are the rings, but actually these are the stirrups. So what is the shape of the stirrups? Can you tell me what is the shape? Is it vertical? Is it inclined? Is it vertical or is it inclined? How we are providing these stirrups? Yeah, in this figure it is more clear. Okay, so how we are providing? Yeah, it is vertical. So this is our vertical stirrups. But later on, when we will discuss about how to design these stirrups, what will be the spacing, that means what should be the distance between the stirrups. In that case, I will tell you what are the different types of stirrups. Actually, we have three different types of stirrups. One is our vertical stirrup, then one is our inclined stirrup. That means you can give some angle, you can provide this stirrup. And the third one is mix, means vertical plus inclined. Okay, so these three types of stirrups we generally provide, but mainly we provide this vertical stirrups. Okay, but in some cases we will go for inclined stirrups also, and in some cases we can provide both vertical as well as inclined stirrups. Okay, so I will discuss this in later parts, but now you see these are the stirrups. Okay, so stirrups means, for designing the stirrups, we have to first calculate what will be the shear force, what will be coming to the structure. Then based on the shear force value, we will first find out what should be the spacing between the stirrups and what should be the diameter. Okay, everything we will discuss later on. But for designing the stirrups, we have to calculate shear force, because these stirrups will resist the shear force only. Okay, this stirrups will mainly resist the shear force. Okay, that's why this is, while this part is known as limit state of collapse for shear. Okay, so let us move to the next part. Then the last part is known as torsion. Okay, so torsion is coming from the word torque. Okay, torsion is coming from the word torque. Okay, so can anyone, do you have any idea, means in a building, say in a slab, in which portion we have to design for torsion? Anyone have any idea? Just use common sense.
Sir, column.
Yeah, good. Near the beam column joint. Okay, in the beam column joint we have to design for torsion. Yeah, good. Okay, so next, these are the different parts of limit state of collapse. That means in limit state of collapse, we have to design our building for flexure, we have to design our building for compression, we have to design for shear, and we have to design for torsion. Okay, and our structure must be safe for bending, compression, shear, and torsion in the first part. And in the second part, after designing all these things, the next part is our limit state of serviceability. So in this part, what we have to check? We have to check deflection. Deflection, I think all of you know what is deflection. I hope I told you also. Deflection, what is deflection? It is the, what is deflection? I think in the first or second class I told you what is deflection. Deflection means change in length. Change in length, if you directly say change in length, it will be said as, it is called deformation, not deflection. Deformation. But if the change in length in vertical direction, that is known as your deflection. Okay, deflection always measured in the vertical direction. When after putting the load, when your beam will bend, so in that case, how much your beam has been bent from the initial position, the vertical distance will be measured, and that will be known as deflection. Okay, so then we have to check cracking also, whether cracking is occurring or not. We have to check that one. Then we have to consider the vibration also. Vibration means, okay, so can you tell me, can just all of you please think about your surroundings, and can you tell me what is this vibration? Vibration means, why we need to calculate vibration, why we need to consider vibration. In every case we have to consider vibration, or in some particular cases only we have to check for vibration. Can you give me an example? Can you give me an example where we have to consider the vibration? Just think your surroundings, whatever you have seen. Okay, whatever you have seen, yeah, earthquake load, moving load, and earthquakes. But every day you see this vibration load, vibrating load. Where? In which case? In which case? Floor? No. No. Where we have to consider this vibration? Every day. If you, while we are going from Panikhaiti to our university, every day you see this vibrating force. Every day. Where? I'm giving you the hint. Just think. From Panikhaiti to our university road. Yes, good. Train track. Yes. Whenever you can see, when your train is moving, you can see, just you can feel that where just near that railway tracks, huge vibration is occurring. Okay, so whenever you are designing the nearby portion of our embankment or nearby portion of our railway track, always this vibration force is the major one. Okay, so we have to consider this vibration. Otherwise, if you don't consider this vibration, and if you just design the road normally for any other part, then it will crack will develop, because whenever our train is moving, it is giving a huge amount of pressure on the soil. Okay, and as a result of that, this vibration will be transferring from the railway track to the surrounding areas. Okay, so whenever we are designing the nearby portion of a railway track, always we have to consider this vibrating force, because this is a major force nearby our railway track. Okay. Okay, so next, our fire resistance. Okay, so our building must be resistant against fire. You all of you know it. Okay, so these things we have to consider. If you have to say that our building is safe, it doesn't mean that your building only safe for against structure. Okay, your building must be safe against bending. Your building must be safe against compression. That means your columns must be same. Then your shear, that means your stirrups must be provided in the safe place. Okay, then it must be safe against torsion, it must be safe against deflection, it must be safe against cracking, it must be safe against vibration, then it must be safe against fire resistance also. Then only you can say that our building is completely safe. Okay, in engineering language, after checking all these things only, you can say that our building is safe. Okay, not only load, because whenever we are designing a building, our main concern is our building must carry the load safely. That is not exactly the 100% criteria. Say that is the major portion, but the remaining things also must be safe. Okay, that means your reinforcement must be placed in proper place, then it must be safe against shear force, it must be safe against deflection. Okay, so while designing a beam, we have to check all these things. Okay, if a beam is safe for all of this, then only we can say that our beam is safe for the construction. Okay, okay, let us move to the next part. Okay, so now here you can see I have said before we are using multiple safety factors. So multiple safety factors given by practicing engineers based on their experience. Okay, so generally we have two types. Okay, load and resistance factor design format and partial safety factor format. Okay, so this first one is used in ACI, that means American Code of Practice, something like that. This factor is considered not in India, it is considered in USA, so we will not discuss about this. Main in IS code, the provision is to use partial safety factor. Okay, so what is partial safety factor and how can you use that? If you read the IS code, you will get in details about partial safety factor. Okay, so now for using this partial safety factor, our main criteria is this one. Our main criteria is this one: design resistance must be greater than or equal to design load effect. That means design resistance means whenever you are putting some load in any structure, it will give some internal resistance. Is it? All of you know that? So our internal resistance must be more than the applied load. Okay, as as long as this condition satisfied, we can say that our structure is safe. Okay, we can say that our structure is safe as long as this condition is satisfied, as long as the internal resistance of the structure is greater than or equal to the applied load. Till that time you can say that our structure is safe. Okay, if the resistance become less than the applied load, then your structure will fail. Okay, so just let me give you an example. So say consider your table, reading table. Okay, say consider your reading table. You know that you are putting some load means in terms of your books, your water bottle, anything, whatever you are keeping in your what means reading table. At this time you can see that your table is carrying these books, your water bottle, your mobile phone, your laptop, these things it can carry safely. Is it? Because why? Because the internal resistance, whatever load you are putting, it is less than the internal resistance. That means as soon as you put a book on your table, okay, as soon as you put a book on your table, that means you are putting some weight on the table. So instantly, immediately your table will give internal resistance. Okay, internal resistance to remain in its own shape and position. Okay, so you know that your capacity of the table is say 100 kg. Okay, so till 100 kg you are putting 1 kg, 2 kg, 3 kg, up to 100 kg you are putting the load, and you can see there is nothing happening in your reading table. But as soon as you cross 100 kg load, that means you are putting say 101.5 kg, you will see that your table will start bending. Okay, and as you increase the load, beyond 100, that means you are increasing 101, 102, 105. Say after 2-3 kilos you will see that your table will break. Okay, so till you can say that our 100 kg is the capacity of the table. That means the internal resistance of the table is 100 kg. So beyond 100 kg, if you put 1 kilo also, it will start failing. Okay, so regarding in our case also, in buildings also, every beam will have some definite amount of capacity. Okay, so your beam will have a definite amount of capacity. That means it can carry a definite amount of load only. So how much it can carry, we have to calculate before constructing a beam. We have to calculate everything, how much your beam can carry, and then based on that value we will put the load on the beam. Okay, and in any case if you see that your applied load is more than the capacity of the beam, you have to remove the load. Okay, so that the applied load will be always less than the capacity of the beam. Then only your beam will remain in its equilibrium, or your beam will be in safe condition. Okay, okay, so let us see the next part. So these are the various what to say, partial safety factors which are given in your IS code also. You can see all these things in IS code. So in limit state we have seen that two types of limit states are there. One is your limit state of collapse and one is our limit state of serviceability. Okay, so when we are discussing about limit state of collapse, so in that case our this gamma means partial safety factor, C for concrete, S for steel. So partial safety factor for concrete is 1.5, okay, for limit state of collapse. It is also given in IS code. Okay, and partial safety factor for steel, it is 1.15. Okay, partial safety factor for steel, it is 1.15. All of you remember these two values. Okay, partial safety factor for concrete in limit state of collapse, it is 1.5, and partial safety factor for steel for limit state of collapse is 1.15. All of you remember these two values, because in any competitive exam or in your final exam also you can expect some questions on that. Okay, then in limit state of collapse, in limit state of collapse, this is ultimate load. When you are considering dead load and live load, when you are considering dead load and live load only, we have to consider a partial safety factor of 1.5. okay, because in designing a building we have to consider live load, dead load, wind load, everything. So if you are considering live load and dead load, then your partial safety factor will be 1.5. Then if you are considering dead load and wind load, okay, wind load, then in that case your partial safety factor will be 1.5, or you can use this formula also, 0.9 into dead load plus 1.5 into wind load. Okay, then wind load or earthquake load. Okay, wind load or earthquake load, then when you are considering dead load, live load as well as wind load, so in that case we have to use a partial safety factor of 1.2. okay, next, these things are given in your IS code. No need to remember these things, only these two things you have to remember. Okay, and for exam point of view, if you can remember these things, then it will be very much good for you. Okay, very much better for you. But for practice, no need to remember this. Okay, and in limit state of serviceability, for every material and load condition, you can see our partial safety factor is 1. Okay, 1 for concrete, 1 for steel. Okay, so you will understand these things when we will solve some numericals. Okay, at present, while I am explaining, you can get confused, but don't worry. When we will solve some numericals, then it will be very much easy to understand. Okay, so next thing, okay, see here how we can use partial safety factors. Okay, so now in the previous cases, means in working stress method, if M20 grade of concrete is given, that means we will understand that FCK value is 20. Okay, that 20 means if you construct a cube, this is a cube of 150 millimeter size, that means 15 centimeter. Okay, 15 centimeter by 15 centimeter by 15 centimeter cube. Okay, and if you keep this cube for 28 days, and after 28 days if you check the strength of this concrete, you in 95% cases you will find it that our compressive strength is 20 Newton per millimeter square. Okay, that is our FCK value. But in actual practice, we will not use directly FCK equal to 20. Okay, because we can't use that directly. So how to use that? You can see first here. This figure, you can see here, influence of size. Compressive strength reduces with the increase in size. Okay, since we are making this cube only 15 mm cube, this is, you can see, this is only 15 centimeter size cube. But whenever you are going for construction, you can't make these cubes 1 cube, 2 cube, 3 cube. You can't add these cubes together and make a building. Okay, so we have to construct this building as a whole. So you can imagine what is the size of the cube. Okay, so as soon as the size of the cube increases, that means as soon as the size of the concrete increases, the strength reduces. You can see compressive strength reduces with increase in size. Okay, so for M20 grade of concrete, if you make this size of cube, that means 15 centimeter concrete, 15 centimeter cube, then only you will get 20. But if you are constructing a huge 1-story or 2-story or 5-story building, you will not get, if you take one part from that building and if you test it, you will not get directly 20. Okay, here it is written compressive strength reduces with increase in size. And how much it is reduces? 1/3. That means 33% has been reduced. You can see here 0.67 FCK. That means only after, when the size increases, when the size of the building increases, then your compressive strength reduces slightly. And how much it will be reduced? It will be reduced by 2/3. Okay, so the strength remains 0.67 FCK. Okay, so after that, this is our, okay, so this one also, this is not our design compressive strength. So to get the design constant, I didn't understand. Okay, so wait, don't understand means, okay, so while constructing a building, you will not go to laboratory. Okay, you will not go to laboratory and you will not make a 15 centimeter cube. Okay, you will make a cube of one slab together. Okay, so you can imagine the size of the concrete. Okay, so in that case your mixing may not be proper, your water may not be proper. Okay, so because of that, as the size of the cube is increasing, you can say that the strength reduces little bit. How much it will be reduced? And after experimenting, we have got that the strength has been reduced by 33%. That means the remaining strength is only 67%. Okay, so it has been written here, compressive stress reduces with increase in size. Okay, so only 67% strength we will be getting. Okay, so what we will do, we will introduce, as per IS code, we will introduce a partial safety factor. Okay, so partial safety factor means we will divide this value by our partial safety. You can see here design strength of concrete will be, this is our actual site condition, site strength divided by partial safety factor. And partial safety factor for concrete is given by 1.5 as per IS 456. Okay, as per IS 456, partial safety factor for concrete is 1.5. So if you divide the value by partial safety factor, we will get the design strength of concrete. Design strength of concrete is 0.45 FCK. Okay, design strength is 4.45 FCK. Okay, thank you. Okay, so next, similarly you can find out design strength of steel. Okay, similarly you can find out design strength of steel. So we write the yield strength of steel by the letter Fy. Say if you are given Fe 415 steel, that means your Fy value is, mean yield strength of the steel is 415. So if you divide the value by partial safety factor as per our IS code, so you will get the design strength of steel, which is, you will get 0.87 Fy. Okay, yield strength divided by partial safety factor. Okay, so wait, I will show you in the IS code also. Let me open the IS code. IS 456. Okay, our meeting will end within 5 minutes, after 5 minutes. So all of you please join with the new link, okay? And I will give you the attendance in the second class only, not now. At the end of the second class only, I will give you the attendance. So if you leave after this class, you won't get the attendance. Okay, you can see the page number. Concrete mix proportioning.
67, sir.
Huh?
Yes, sir, 67.
67. Okay. Okay, page number 67. This is our limit state method. Okay. Wait. No, I'm searching for this partial safety factor.
Sir,
Ah, yes.
I see in page 68,
68
table number 18.
partial.
That
Okay, clause number.
clause number, I don't know. Table 18. It's written
Table
good use
18.
of partial safety factor. Yeah.
Okay, wait. Partial safety factor. Actually, I don't have, at present, I don't have the IS code, hard copy of that IS code. That's why it is difficult. Yeah, limit state method. Yeah, this one. See this one. This is your table number 18. Yeah, this is our partial safety factor. Okay, so the design strength of material is you can find out by using this formula. This is, you can see here, characteristic strength of material divided by partial safety factor. Okay, so if you are considering steel, so it will be 0.67 FCK divided by partial safety factor. Okay, so 0.67 FCK divided by partial safety factor for steel is 1.5. So you can see here. Okay, for concrete it is 1.5 and for steel it is 1.15 partial safety factor. Okay, so design strength, you can find out design strength if you use this formula. For concrete, in place of F you have to put 0.67 FCK divided by partial safety factor 1.5. Then in that case you will get the value 0.446, or if you write in 2 digits you can write 0.45 FCK. Okay, and if you are using steel, okay, because in RCC the main two materials are, you can see here materials is written. So materials means we have only two main materials, one is our steel, one is our concrete. So if you are using concrete, then it will be 0.67 FCK divided by 1.5, that is our 0.445 or 0.45 FCK. And if you are using steel, then it will be Fy divided by gamma m, that means Fy our yield strength divided by our partial safety factor is 1.15, so you will get 0.87 Fy. Okay, and these two values only we will use while designing any structure in limit state method. From now on for the remaining part of the syllabus, whenever you are designing, whenever you are considering the design strength, then you will say 0.45 FCK for steel, for our concrete, and 0.87 Fy for steel.